Okay. Good morning. Yeah. This is the first course of the application acceleration with the high-level synthesis. I believe you have noticed this course is going to be lectured in English. So, however, that it's going to be an interaction in the class. So you will read question or answer question. You are free to answer in Chinese if it's more comfortable with you. And first, I don't use a microphone. How about the person in the last row? Can you hear me clear? Okay, not clear. Oh, okay. I'm going to lecture 6 hours per day. I bet I don't have that much energy. I try to speak. Otherwise, you come close. Yeah, come close. Yeah. Okay. Yeah, I encourage you. You sit in the front. Okay. Yeah. Okay. So I will ask for those people, for those online. Can you hear me? If you can hear me, raise your hand. Okay. So does anybody raise hand? Okay, good. Okay, so okay, this is the agenda I'm going to go over today. Yeah. First, I will give you an overview from industry point of view, so that you know what the benefit you can learn from HLS and how the industry use HLS. To tell the truth, Taiwan is probably coming late in the HLS education. And the other side, in China, they have been working on HLS for some years, and they have a very a lot of activities going on for HLS. For example, like Xilinx holds twice a year in Beijing University for a week or 2 weeks HLS education for hundreds of students. Many of the college in China, they actually have a HLS course. Yeah, but none is in Taiwan until last year. And so Taiwan is strong in IC design, kind of leading. But I'm worried that with the new methodology comes in, if we don't adopt fast, we're gonna be behind. Yeah. So that's the reason why I like to teach HLS in the school. Yeah. For me, you know, I come in from the ancient world. Okay, the world people still design with a schematic drawing. Yeah. And then I probably is the very early stage of an engineer using the Verilog, and probably the first tier of an engineer using the synthesis tool. Yeah. And the HLS actually I just learned it 2 years ago. Yeah. So it's pretty new and it's still evolving. Yeah. A lot of material keep updating. Yeah, for example, for this year, you're going to use VTIS 2021.2, which, to tell the truth, when I decided to use it until now, it's also a version late. Okay, so it's moving fast. For each new version, they add new features and make its HLS compiler more powerful. Yeah, so for any course like this, you have to keep up all the time. Yeah. Okay, and then and next I will have a TA to give you an instruction on the lab of logistics. Basically, how you're gonna to log in to use the Fpga, and you are not going to have a Fpga board on your side. We put all the Fpga in the lab, so you use the FPGA through your notebook, remote logins. Okay. I think today that's cloud computing. Okay. Everything, yeah. All the computation is done in the remote side. Yeah. So it's good that everybody can share the facilities and it saves the maintenance of the boards. Yeah. Okay. And then next, I'm talking about the course plan. That's the work that you can expect in this semester. I'm not sure I have a time to cover the next topic, from logic gate to HLS. From my experience when I was teaching in Taida, I don't have time to cover that. Basically, it takes you through the logic design process and all the way to the HLS coding. So give you an idea how the HLS can drastically reduce the design efforts. Yeah. Okay. Cannot open file. Why? What's happening? Use this one. Oh, I can use this one. Okay. I don't know what's happening. I cannot edit. Oh, yeah. Oh, okay. Okay. So the name of the course, the application acceleration with high-level synthesis. Okay. From the title of this course, there are two things you have to pay attention. One is application acceleration. Okay. I'm not just teaching a function acceleration. Okay. Keep in mind, we are talking about application. Okay. So for you taking the course at the final project, you're gonna do the end-to-end application acceleration. So everything has to stem from the application point of view. Okay, don't just simply accelerate the kernel functions, because when you do the application accelerations, what you're gonna to optimize is much more than just kernel functions. You have to taking care of the communication from software side and the kernel function in the FPGA side, and that's actually play a much more important role than just optimize the kernel function. I can take an example. A few years ago, when Microsoft first put their FPGA in their data center to accelerate the Bing searching engine, and the kernel function actually can speed up about 2 orders, more than 100 times faster than running in a server software. But when they put it into a system, the overall acceleration only 2 times. Okay, so they still have a lot of work to do to make the application acceleration really meaningful. Okay, so in this course, since I'm coming from the background, not just from the IC design, I actually doing the system design. So I'm quite emphasize on the system level optimization. Okay, so do expect when you do optimization from the system level point of view. And second is high level synthesis. In here, particularly, I'm talking about C, C++. And I will not teach OpenCL because Intel FPGA using OpenCL. But OpenCL is much restricted. And C and C++ give you much more freedom, flexibility to design a better accelerators. Okay. So I give you a little background about myself. So I graduated almost 40 years ago. So that's why I said I come from an Asian world. Yeah. And later on, I went to UT Austin to get my master's degree. And then after graduate, I went to Silicon Valley. My first job is LSI Logic. At that time, I was working on software, the EDA tool, particularly the placement tool. Yeah. And after 2 years, and at that time, I decided whether I want to do the Unix kernel, because the Unix just open source, and a lot of people working on the Unix kernel, yeah, the software, or I do the IC design. And I was rejected by the company working on the Unix kernel because, you know, from Asian people, yeah, how can Asian people know the Unix kernel? Yeah. So I went to a startup company doing the chipset design. At that time, you know, the PC was invented by IBM like 1980, 81. Yeah. And so at that time, it's 1989, that a lot of PC chipset or the PC is still evolving. Yeah. So I was joining the PC chipset company Symphony, which is the predecessor of VIA technology today. And later on, 2 years later, I, with my seniors, founded VIA technology and moved the company back to Taiwan. And then for VIA, you know, VIA working on the chipset for a long time. And then we acquired a processor, x86 processor. And I did the technology transfer from UT Texas. From Texas, moved the x86 processor to the Beijing research R&D team. Yeah. And right now, that processor is adopted by China. That means the machine using the VIA processor can be used in China government. Yeah. So after that, I working on the SSD controller. Okay, SSD controller is quite a different animal than chipset and processor. Okay, chipset and processor, basically you follow a strict spec. For chipset, you have to follow all the bus interface spec. For processor, you have to make sure the architecture design that conform to the ISA, instruction set architecture spec. Okay, so every cycle, you have to get the exactly result, okay, from the ISA specifications. So at that time, there's pure hardware design, okay, no software whatsoever involved. Okay. But SSD controller is different. SSD controller, actually, the whole thing is a piece of software. Okay, you take the transactions and you do all the algorithm computation, and then you try to get the object from the drive as fast as possible. Okay, and so that's why for SSD controller, the whole chip architecture is defined by software guys. Okay, so first they have the algorithm and they partition their algorithm and seek what's the crucial part of the whole process. Then they ask the logic designer to accelerate that part of functions. So software guy define the spec, and then the hardware does the implementation. Yeah. So that's a SSD controller. And later on, since SSD controller is still a wall of IC tape out, the cost is really high. So for company, they don't have much funding to tape out chip, especially, let's take an example, why China can catch up the IC design, because China, the government sponsor all the tape-out fees. So they can choose the most advanced process. Okay. And so if you don't use the advanced process, So no matter how you crank your design, how you push your power down, but it's simply hard to compete with a design using advanced process. They give you a much smaller dice. That means the cost is lower, and then the power is lower. Okay. So for a company doing the IC design, it's really hard to compete if you don't have a lot of money to burn. Yeah. So at that time, I moved to the system. Yeah, because system design is more of your brain. Okay, you optimize system, a lot of intellectual involved, and then you create value based on your intellectual. That's why I think that is much more valuable for engineer. Okay, so I moved to the system design. At that time, we designed the storage system, in particular, distributed object storage system. Okay, for object storage, basically giving you a object ID, for example, 256 bit of object ID. And then you try to find out, locate, and retrieve the object from billions of objects in the drive. Okay. So at that time, I find out that, for example, like IPFS, I don't know whether you heard about that. In today's the metaverse, all the objects were saved in the world, and people use IPFS storage. That's a distributed storage. IPFS means interplanetary storage system, 的星际网络档案系统。Okay. So we did an experiment that when you have a object occupy maybe 10 gigabytes of data in the storage, you can retrieve the object very fast. But if you put terabytes of objects in a drive, when you try to retrieve it, they slow down quite significantly. Yeah. So how do you retrieve the object fast? Okay, it's you're gonna need a very advanced algorithm. Yeah. So basically, that's a kind of a searching and sorting algorithm, and however, you have to implement in the hardware. So when at that time, we still follow the traditional design flow. That means the software guy define the spec, and then give the spec to a logic designer. Okay, a logic designer implement the design, but the problem is you could not write a design spec clear enough so that people won't misunderstand it. Okay, and there's hard time for logic designer to do after the module design that you need to verify. They don't have a capacity to do that kind of verification because the system level, they don't have an idea about the surrounding. They could not generate the testing data. So it always happens when they deliver design, put into the Fpga and run in the system. Also, the bug happens. And who's going to debug this system? The software guy. But it's very difficult for software guy to debug a black box because that design is not designed by him. So this kind of process iterates for a few months to finally get the system settled down. And then you can start test the performance. Yeah. So it's quite annoying at that time. And that's about 3 years ago. I happen to know there is a high-level synthesis in the market. So I told the software guy, why not you design your hardware? Yeah. So at that time, we start experimenting the HLS. And in the first, when the first design by the software engineer, and the performance is very, very low, and the gate count resource used way higher than the logic designer, senior logic designer. However, after 3 months, they use adjust the pragma and even change the coding a little bit. they can come to a design that performance like an equal, and the gate count is more or less the same as the senior logic designer. So I think this design flow, design methodology is quite promising. So that's the background why I come to school to teach this design methodology. Yeah. Okay, yeah, so this is background. And so that's the topics I'm going to talk about in this slide. Okay, first, the whole industry or even the US government realized there is a need for software-defined hardware. How do we know that? Okay. Okay, DARPA. Okay, DARPA is a government agency who funded the U.S. Research program that to meet the Defense Department of Defense needs. Yeah, and so a few years ago, I believe that probably 4 years ago, they have a program called Software Defined Hardware Program. And its charter is that in the modern world, decisions are driven by information, the ability to explore data, to understand and predict the world around us is an asymmetric advantage for the Department of Defense. I really don't understand why use the asymmetric advantage. That means that only US have this advantage and others could not have. Yeah. So I think it's very clear. A few days ago, I watched a movie talking about Alan Turing, who invented a machine to break the German code. Okay, and then with his effort, they can reduce the World War II 2 years. Yeah. So I think you can well accept these statements. Okay, but what you need really pay attention is the following two goal of the software-defined hardware. Okay, first, they emphasize the compute efficiency. Okay, that means the giga operation per watt. Okay, they define the goal is within 5x of H chip. Okay, and more than 3 orders than the CPU. Okay, in here, yeah, actually that's a compound matrix. Okay, it's a giga-ops per watt. So you don't simply push the giga-ops. Okay, that's today's approach, like a supercomputer. They put cluster a lot of servers. They simply crank out more giga-ops. Okay, they don't care power. Okay, but for power, it's really a big problem. In today, if you know, when you use Google to do a single search, how much power gonna consume in the data center? A lot of work, okay? And so all the economic activities rely on intelligence, and intelligence rely on compute. Okay, if the compute consume too much power, then they are not going to be able to support the goals of the economy. Yeah. So the power is very, very critical. Okay. And the second goal is the programmability. Okay. In here, the software-defined hardware, basically, we are talking about FPGA at this stage, programmable device. Okay, of course, they are trying to invent new material which replace the FPGA, but until now, or even after in the future, it's still using the FPGA. Okay, and FPGA basically is a hardware design. Okay, you write the software, but basically you are programming the architecture. Okay, you are not programming just the application. You're programming the architecture, doing the actual hardware design. Yeah, and so another goal is you want to program this FPGA programmable device as easy as using the Python. Okay, so you can think why Python is easy to program compared to like a C, C++. Yeah, what factors that make Python easy to program? Yeah, and the same concept going to be applied to HLS, the software-defined hardware. Yeah. Okay, so there are three high-level observations. First, the computation power hit a plateau. Yeah. We know that there are, from my point of view, I think that there are two factors that the power really a big issue. First, today's computer architecture, the low stall type of computer architecture. Today's the processor or even the GPU, they are all based on the low stall architecture. Why it is a low stall? Why people adopt a low stall? Because it's flexibility it provides. Yeah. Then all the data can be kind of once you when you run the program, it involves the data synchronization. Okay, and the data synchronization is running in dynamically. It's very hard to control. So you want to temporary buffer save in the memory. So make the code execution easier to handle. So low stall architecture is a bottleneck. And later we will see why it creates a lot of power. The second problem is in today, we are still shrinking the process. We are still be able to crank more transistors into a die. However, since the process shrink and you crank more transistors, the bottleneck is the power. Okay, and for deep submicron process, the leakage aggregate by temperatures. The power creates a higher temperature, and the temperature create more leakage, and leakage create more powers. So the silicon simply breaks down. Yeah. So for that reason, maybe you hear about dark silicon. That means not all the logic in the die running at the same time. Okay, you have to make certain part of the die inactive. Okay, in order to maintain the power consumption within an envelope. Okay, so that's the reason that even though you can put more transistor, but it's simply hard to increase is computation powers. So that's the problem. So for that, the general low stall computer architecture could no longer enough to solve the problem. So we need application-specific architecture to solve this problem. And the last one address the second goal. You want to program the FPGA device as easy as the Python. Okay, and now let's go back. When you do the Python code, actually you call a lot of package, a lot of functions. You don't actually implement the detail of the function, you simply call the function. So in terms of the hardware, that means the IP design. Okay, and in traditional hardware design, if I start a company and then I want to tape out a chip, and the chip is so big and needs so much IPs, so what we do is we license the IP from third parties. Okay, and then you have to pull a front feed. Okay, so it's called NRE. Okay, so they release the IP to you, and then you can integrate and start doing the testing. Okay, so before you can really get any work going, you have to spend a lot of money to license the IP. But in today's you can get the IP from the marketplace, and actually every one of you, if you have a smart algorithm, you have a better design to run fast and low power, you can put your IP in the market, and people will buy it from you. And before, you cannot do that. And when people try to download IP to do the test, you have to pay the money. Okay. You pay the money only when you integrate the IP and put your application in the cloud, and they start charging you. They start charging you when you are generating income, then you pay for the IP. Yeah. So it makes the people doing the customer design, the barrier is much lower. Yeah. So everybody can do the design. Yeah. And use those IP. Yeah. Okay. So in today's computing device, you all know that we have a CPU, we have a GPU, Fpga, and at the end, the ASIC. Okay. And ASIC, I gonna to drop that topics because the ASIC, because of its long development time and much higher cost. So in the future, I believe it's not like Taiwan 20, 30 years ago. A lot of startup companies, like my engineer, many of them, they went to start their company at that time. But today, it's very difficult to start the IC design company. Yeah. So in the future, I think only those very big IC design companies, they have the enough funding to take out the chip. Okay. But that doesn't mean we are not going to have a less AC designer. It's wrong. The AC designer is still in a big need, but you can only spend work for big companies. Okay. You probably don't have much chance to start company doing the IC design as before. So let's only focus on these three, okay, the CPU, the GPU, and the FPGA. And we look at these two. One is the relative performance, okay, and that's for GPU is 2 order than the CPU. And for FPGA, the performance is the another order higher than GPU. Okay, and there's a paradox here. We know FPGA is hard to run at a high speed. Okay, for GPU, you can run at 2-3 gigahertz. For the FPGA, you probably run up to 300 megahertz. Okay, so in terms of clock speed, it's 10 times difference. And why you can still achieve better performance. Okay, you really need to think about this question. Yeah. And next thing we need to think about is the ease of programming. Okay, we know CPU is the most easy to program. Okay, and then the GPU. But today, if you do high performance computing, you probably all learn the GPU design, the GPU programming. Okay. But for FPGA, it's hardware design. So very real people have a hardware design experience. Okay. So here, I simply very quickly brief through the various architecture of these three devices. For the CPU, the noticeable, you have a low store unit, and then you have a instruction cache and data cache, and then you go through the instruction pipeline stage. Okay, and at the execution stage, for each CPU, you have a fixed number of computation elements. Okay, so either the compiler or the processor architecture, they try to optimize to improve the utilization of the function unit. That means they want to run the instruction pipeline as without store. Okay, so they want to increase the pipeline utilizations. So there are also the very complicated algorithms to improve its pipeline utilization. For example, smart cache, because you don't want the pipeline waiting for the data. So they have a complicated cache design. And they have multi-issues. Okay, you make sure you have enough instruction string SQ at the same time to fully utilize the function unit. And then you have out of order. Okay, when the instruction waiting for data, you want to be able to schedule another instruction. So for those very complicated architecture, your purpose is increase the IPC. That means every cycle, how many instructions you can execute. That's at that time, that's the sole index for the processor architecture design. So when a new processor architecture comes out, people ask, what's your IPC? Okay, so that create a problem that, and then later on, people say, oh, I probably not just simply look at that, because with the high IPC, but I run low frequency, it turns out the total computation power does not increase. And then later on, people try to increase the frequency. Okay, I remember that's a P4 processor. Okay. And then in order to run high frequency, that you need more pipeline stage. And more pipeline stage, once it's stored, okay, I mean, there's a contention happen, then you have to store the pipeline. Okay, so the deeper the pipeline, that the contention create more penalties. So it's a paradox. Okay, and then people got stuck. Okay, so the architecture at that time, then people then resort to multi-thread, and later on the multi-core. Okay, that's today's processor architecture. So I just simply give a very brief history. And then at that time, graphic user interface is important. So at that time, there's a graphic processors. Okay. And later on, NVIDIA, and they find out, oh, actually, the graphic processor can be used to solve many scientific computation, because they have like a pixel shading. Okay, those things actually that's basically the SIMD like architecture. Okay, so all the computing element execute the same instruction. Okay, with multiple data streams. Okay, that's very good for scientific computation. So later on, they use their processor chip to solve physics problem. So that's called general computing. Okay, so the GPU. So from their chip, it's noticeable that you have a dedicated accelerator, like handling the display, handling the video. Okay, yeah, for those it's hard-coded because they have a standard. Okay, for those Q computational parts, like a pixel shader, those things that they generalize into an array of compute arrays. Okay, and today's and this kind of structure also good for today's neural network acceleration. Okay, so for neural network acceleration, fundamentally it does the matrix vector or matrix multiplications. Okay, so that's very much like the similar to the GPU architecture. Okay, and that's the FPGA. Okay, FPGA, that's a sea of an array of the large block, and specific for DSP and the memory, all in an array. Okay, and then the way they are interconnect is programmable. Okay, with the programmable interconnect, that you can form customize the data path. Okay, and later on I will talk about data flow architectures. Yeah. So for data flow architecture, the data path has to be customized. It does not like the GPU and CPU internal the connection and the function unit, the interconnection are fixed. So that means the data path is fixed. But for different algorithms, different computation, you need different data path configurations. They cannot do that, so they use the load store to accommodate different data flow. Okay, so that's in this diagram. So we can see this N is programmability. So CPU give you the most flexible programmability. But in terms of silicon efficiency, the ASIC give you the best, and then the FPGA. And in today's modern supercomputer, people use the CPU and GPU and the hybrid of these two. Okay, and this three category device is a software. Okay, and the FPGA and ASIC people regard as the hardware design. Yeah. Okay. I think this diagram will give you a better idea why we are so like the FPGA. Okay, first, there's a breakdown on the operation and the memory access. The power is measured based on 45 nanometer 0.9 volt. Okay, so this part, that's the computation. Okay, and that's the memory. And memory you can think is data movement, the power used for data movement. Okay, so for load store architecture, okay, you either store the data in the architecture registers. Most of the time, all the data used once. You actually get the data from the cache. First, you move the data from system memory. Okay, from system memory is terrible. The power 32-bit data get from the DRAM consume a narrow joule. Okay, that's why we need to use the cache, because when you access the cache, like a 32K byte cache, that's a 20 picojoule. Okay, and today's processor need a bigger cache, probably in the size of a megabyte, and that's 100 picojoule. But for doing integer, 32-bit integer adder, is only 0.1 picojoule. Okay, this number is very critical. Okay, before we are doing design, we want to optimize the computation. Okay, and today you have to shift your focus on the data movement. Okay, so that's the soul of the architecture design. Yeah, so let's say in today's the neural network accelerators, when people publish papers that I have this device and I can run a certain frequency with how many teraflops computation power. Okay, and this number, to tell the truth, simply tells you how much resource they allocate in the chip. It doesn't give you the real performance. Because for those teraflops, the second question is, why is your utilization? Okay, how much time you can keep those computation units running instead of idling for data? Okay, so when you're talking about performance, don't simply look at how many teraflops. Okay, you have to look at, can they efficiently use those computation resources? Yeah. So in summary, this is a summary, okay? So for processor SQL instructions, they break down the energy consumptions. For cache access, they spend 25 picojoule and register 6 picojoule. And then you have all the pipeline control logic. And then you add up, for SQL, a single instruction it takes 70 picojoule. Okay, within that, the real computation only like 1 to 3 picojoule. So today is when we talk about application acceleration, so it's really a data flow management problem. Okay, so that's the majority part of the whole energy spent there, the data movement. So today I talk a lot about concepts, and those concepts should be merged, integrated when you are doing the design. Okay, focus on what's really important things first. Yeah. So this is another study. Okay, they do a lot of application, and then they try to compare the computation density per watt. Okay, so that's the goal, the DARPA setup. Okay, the one of the goal. So for big operations, we know this from this one. The 2N on the right hand side is the Xilinx FPGA. On the left hand side is the Altera FPGA, and in the middle is either the CPU or the GPU. Okay, so we can see the gigaops per watt, and for big operations, definitely the FPGA device has much advantage compared to CPU and GPU. But even though for native data type of GPU, 32-bit floating point operation, that's what the GPU internal design for. Even though with that, the FPGA still better than the GPU. Okay, and remember the GPU is a silicon. Okay, and the FPGA is a programmable. They have an intrinsic device overhead there, but you still get a better gigaops per watt. Okay. So you may ask, even though with the GPU native data type, the FPGA still outperform the GPU. Okay. Yeah, so that's the question. GPU run 1/10 of FPGA run 1/10 of a GPU and CPU speed. So now you should ask yourself why FPGA is more compute efficient than GPU. Yeah. First, a lot of computation is irregular parallelism. Yeah. And GPU is not good for that. Yeah. And also, all the GPU and CPU, they handle pre-wire data type. They support like integer floating point. And it's not like a FPGA. You can have a customized data type. So for certain algorithm, when you do the detailed analysis, you may find out to meet your accuracy requirement, you probably need certain bits operation. For example, maybe you just need 17 bits that can meet your target spec. But with CPU, then you have to use the 32 bits integer operation. And for FPGA, you can customize design a multiplier with 17 bits. Yeah. And also, for the FPGA, you can customize the data path using the data flow model. And what's the more important in this class, in the second part of this class, this course, we will introduce a FIN. That's a framework to design the neural network accelerators. Okay, for that framework, you are allowed to design different bit widths for different layer of the neural network. Yeah. And in the last semester final project, that a group of students, a team, they actually have a target accuracy they want to achieve. And then they fine tune the bit width in each layer. The purpose is they want to feed the VGG 19 to pink FPGA, but we know pink Z2 has like a 80 something K, 80K lab. Okay, so they cannot accommodate too big of a neural network. They try to fit in that, then they adjust the bit width for each layer of the neural network so that they can fit in and then achieve the target accuracy. But for fixed architecture, you cannot do that. Yeah, so that you can get really low power edge device. Yeah. So FPGA gives you a benefit to provide a customized data path. Yeah. Another one is important. There's an efficient memory access semantics. As I said in previous slide, you know that the design actually is the data flow management problem. So how do you access the data? Okay. And for a program that, for example, when you compute the data, you have a certain data pattern, access data patterns. Okay. So most of the algorithm has either temporal locality or spatial locality. So for that, if you can observe or find out the access pattern with the locality, then you can design a special buffering or cache algorithms to capture the data earlier or safe in a fast on-chip memory. For those design techniques, you can greatly reduce the access time and reduce the power. And that's only the FPGA customer design can give you this benefit. And for processor, for example, you have to rely on the processor architecture. Okay, you know, in modern processors, they have a instruction called prefetch. Okay, so that you have to, in your write your code, if you know in the future you're gonna to access the data, you can prefetch the data, put into the cache, so that in the later compute stage, then you can quickly access data from the cache. Yeah. So the mechanism to access memory subject to the processor architecture is not up to your programmers. They only give you very limited control on that, like the prefetch instruction. Yeah. A lot more other complexity, complicated mechanism that you could not use a simple prefetch instruction. Okay, so that's why I can conceive why FPGA give you more compute efficiency than the GPU. Okay, so now the next question is why FPGA is not as popular as the GPU. Yeah, I think this answer is quite straightforward. Yeah. Okay, next one, that's from the market that FPGA is already in cloud for a while. Okay, first, Microsoft, I just said that Microsoft put their FPGA in their data center to speed up the bin search. Amazon put their FPGA in cloud to offer to the application developer. Okay, Amazon put the GPU for a long time, so a lot of application, they want to speed up their application processing, they use the GPU. And right now, like this happened in 2016, yeah, like 5-6 years ago. And a lot of application developer start to speed up their application using the FPGA in the cloud. Okay, with those efforts, actually in Western, in US, that a lot of software application developer has the capability to program the FPGA device. Yeah. So for this course, I intend one of the objectives for this class is to enable software engineer to develop FPGA design. Yeah. Then, so the question, who uses the FPGA in the cloud? Okay, basically it's an application developer. Yeah. Okay, so now the next question is how can we make the FPGA development easier? So for software engineer, when you talk to them, that what do you think about the FPGA design? Basically, they will tell you the following difficulties. First, they think the hardware language, like the HD hardware description language, mainly the Verilog, is too low level. It's very difficult. Okay. And next, they will say, oh, we know nothing about the hardware design. Yeah. And another question is when the application originally is a whole piece application program. Right now, you have to partition part of the application program and have it running in the FPGA. So the next question is how do you communicate between the the application program and the serrated part of the function? That's another difficulty. Okay. So to answer the first question, hardware languages are low level and very difficult. So fortunately, today we are talking about using C, C++ to doing the design. Okay. And for Python and TensorFlow, they have a compiler to compile part of a design into the FPGA. For Python, you don't use the Python to write the serrated functions because the Python is typeless. Okay, and Python, the language is too freeform. It's very difficult to have a compiler to do a good job on it. Okay, and for Intel, they use the OpenCL. Okay, but OpenCL is not quite flexible. And Xilinx originally support OpenCL. Okay, I believe 2019, before that, they support OpenCL, but they later on dropped. Okay, today they only support C, C++. So in this course, we only teach the C, C++ for high-level synthesis. Okay. So this will give you a very preliminary idea how you write the code to generate FPGA design. In here, that's the design you want to do. Okay, you have a video streaming in, and then you have after doing the computation, basically the video processing down in the hardware and write a result to the DRAM. Okay, in the whole data path, you use the OpenCV library. For these two parts, you simply call the OpenCV library. And the OpenCV is written in HLS. So it's ready to synthesize into the Verilog code. Okay. So just like you write the Python, you call the OpenCV package and simply call the function. And in between the function that you probably need to do some kind of processing, which is not available in the library, then you write the code, C++ code. In here, you write the flow control and normalize these two functions in C++. Okay, so that you already save a lot of effort to to write the whole thing in, save you to write the whole thing for the whole data path. So that's the C++ code looks like. Okay, you have a function declare, and then one thing here is you use a lot of pragma. Okay, so in this course, we're gonna teach the pragma. Okay, but that's not the main purpose of this course. Okay, but it's an important part. If you know the strengths and weakness of the each pragma, then you use the pragma to instruct HLS compiler to do a job for you. Okay, and inside you call the existing function library, and then you only develop these two parts functions. Okay, so you can quickly develop the hardware design. Yeah. And then going through the HLS compiler, then you load the compile executable code into the Fpga. Yeah. So this is a very brief idea. Yeah. How you develop the HLS application. And in here, to speed up the development, Xilinx provide a lot of libraries. And the library has various application areas. Okay, there are some core library like doing the math, linear algebra, statistics, DSP, data management. And on top, you have a different application area. And people use a lot on vision and image. And Okay, okay, yeah, you can hear. Okay, good, good. Yeah. Yeah. Okay. First, the data level parallelism. Okay, like your SIMD is a type of data level parallelism. Okay. Another is for a workflow involve multiple process. Then you use the test level parallelism. So that's a typical pipeline. Yeah. So going these directions. Yeah. And the data parallelism is this span the data set in these directions. Okay, so today's software programming, people all use these two types of parallelism. Okay, and then for the instruction level parallelism, mostly this part of a parallelism is handled by the compiler. Okay, and for example, in HLS, there's a for loop. You can always enroll to make those operations run in parallel. Okay, and data level parallelism and text level parallelism, a lot of time you need to coding in your software. Okay, so I don't think the hardware design, because the hardware design fundamentally is a parallel programming. Yeah. Okay, the remaining question is how software application interact with FPGA. And the framework to enable the FPGA communicate with host program is already provided by the FPGA vendor like Xilinx, Terra. Yeah. Let's look at this example. Originally, you have the application program, these parts running in the host processors. And then you identify the kernel part of the application program. That means the function that spend most of the time. Yeah. So you put that, identify that as accelerated functions. Then you want to move this accelerated function to FPGA. Okay. Before that, this two part of the program, you interface with a function call. Okay, and then you communicate the caller and callee by the argument. Okay, the argument is saved in the stack, and stack is in the is in CPU cache. So you communicate with a local memory, shared memory. Okay, but once you move the accelerated function to FPGA, how do you communicate? And also the data set, the data set often shared by the host program and the accelerated functions. They work on the same data set in the same address space. Basically, probably you running the data in the cache. Yeah. So you move the accelerated function to FPGA device. You have to hand over the data set to the FPGA in order for the FPGA to compute. Yeah. So how do you do the communication? How do you do the data movement? So these things you need infrastructure to support. Okay, the infrastructure include two parts. Okay. One part is here running in the host side. The other part is a hardware function running in the FPGA. So for host side, you need to have an API so that the host program access the accelerated function just like you did before. Okay, you use the same function call. Okay, transparent to the host program. So that means you need to have a set of API. Okay, provided for the host program to use. And then for the data movement and synchronization, you need a runtime or the driver. And this part is actually talking to the hardware. And this part talking to the software. And these two parts together to link the host program and the authoritative function. Okay, so in the FPGA side, the authoritative function again need to, as before, this is a function originally in the host program side. You communicate with them. So right now you communicate with the XI interface. Okay, it's a bus interface. So that's important to understand this relationship, because when you doing the high-level synthesis, there's a function argument. Okay, the argument is used to communicate with the host program, and that argument has to be translated into the actual bus. The bus here is the XI interface. Okay, so for this authoritative function, you communicate with using the XI interface. Basically, the communication is through the function argument, but you have to define the argument map to the XI interface. And then involve the data movement, you use a DMA. But how the data, the DMA is programmed and get running through the driver here. And these two parts, before, if I have a start company, before, if I'm a system company design the FPGA card, then in addition to hire the hardware designer doing the FPGA design, I have to hire a driver guy doing the system programming. Basically, I need people, staff to handle this part. Okay, but this part, right now, the FPGA vendor provide all the infrastructure for you. Okay, so if I want to design a FPGA accelerator card in the company, maybe 1 or 2 people can deliver product. Okay, you leverage all the infrastructure built up by the vendor. Okay, so right now, after this done, so there are 2 issues happening here. Okay, one issue is the data movement. Okay, if you recall that data movement is very costly, right? Yeah, from the very beginning. Right now, you move the authoritative function to FPGA. You have to move data from host side, from the cache, and then going through the I/O bus like PCIe. It's take a longer time and consume a lot of power. Okay, so do you really gain by accelerating the function by moving to the FPGA? Yeah. So since it's not that straightforward. So when people publish a paper, you can see very real people talking about system benefit they got. Okay, they publish a paper, say I have a function originally running in software on the CPU, and it takes that much time, consumes that much power. And then I put a kernel function to FPGA, I reduce time and reduce the power. Okay, to tell the truth, they really don't tell the whole story. Yeah, the whole story, as I said, you have to move data over there. They don't come into that. Yeah, that's an additional data movement. Okay, but I'm not saying that the whole thing doesn't give you any merit. So that's the critical thing is, how do you do the system design to minimize the power consumption and to hiding all those data movement latency is introduced. Yeah. At the end, you calculate the net power, and you still gain, and the performance still improve. Yeah. So there are a lot of system design techniques and tricks here, to minimize all the overhead, and either hiding or to use some kind of method. For example, when I move data, okay, one technique, as I said, computation is cheaper than data movement, right? So obviously, there's one technique, you do the data compression. Okay, once you do the data compression, you move the data faster, and you use the computation, because computation is cheaper, right? Yeah. So that's another simply one techniques. There are a lot of other techniques that you can, really get the net benefit from this effort to move things to host to Fpga. So that's the data movement overhead. The second thing is this part, when you access, they are running the same address space. Okay. And once you move over here, this guy is using physical address. So the host program and this device actually running in two different address space. So that's another overhead. Then you have to do all the address translations. Yeah, in order to do the communications. Yeah. Okay. So that's the question I'm giving to you is, moving function to a Fpga actually creates a lot of overhead. What happened? Yeah. Can we really gain performance and reduce power? Okay, before, let me see. Okay, I intentionally create this question because I want to make sure whether every one of you still wake up. So I will point to someone to answer the question. And for the third question, when some function move to Fpga, what statement is true below? Okay. So can anyone volunteer answer the question? So how about that corner one, the last row? Right. Yeah, yes. Can you answer the question? What statement is true? First, the actual test synchronization overhead is true, right? Okay. The second is the actual data movement, right? The third one, host software and Fpga function cannot run in parallel. False. Yeah, of course they have to run in parallel. Yeah, otherwise, the CPU just idle, do nothing. Then that's the main part that you gain. Yeah. Okay, good. And overall system power is reduced. Tough. The answer depends on who designed it. Okay, good. Okay, yeah, so let's move on. Okay. We like to design the hardware in a software approach, like similar as we do the software programming. But in reality, that's not the story. Okay, that's not true. So in here, I will point out two issues, yeah, which is different from the software program and hardware design. Okay, first is data dependency. Okay, so when you write the code, like this code, okay, so there are three types of data dependency. Normally, if you take a computer architecture or compiler course, that's the main topics about the data contention. Okay, so there are three types of data contention. 是什么意思？哦 ，OK， I see。Data dependency. There are three types of data dependency. One is the read after write. Okay, another is write after read and write after write. These two these two are not the true dependency. I will suggest there's a very practical practice that you write the processing of each step in this manner. Okay, and so 我这里吗？哦 ，OK。So this slide, I don't intend to be too technical. It's supposed it's a industry perspective, yeah. But I do need to point out certain things that you know that when you develop the HLS, quite different from the true software development. Okay, so when you write, if you are a software developer, when you write this code, okay, you never need to worry about data dependency. Like this example, okay, then if you write this code, and normally I will do that, then you have in the x-axis, that's a time step. You simply list each step, okay, and then there's each one take one cycle to get the array input and do the multiplication, and then you store to array. Okay, and the vertical is across the iteration. So the in the x-axis, that's the intro loop. The vertical is inter loop, across loop. When you try to lay down each step, then you will find out one thing is like here. You want to input A1. However, the A1 is get updated in next cycle. So that's a read after write dependency. Okay, so for this type, the next iteration cannot start until 3 cycles later. So store A1. So this second iteration can only start here, because after you store and then you read it again. Okay, so that's a code I equal 3, the interval, initialization interval. That means next iteration can start 3 cycles later. Okay. So you never, for software guys, you'd never be aware of these situations. Okay. And the next one, right after read or right after write. These two things not the true dependency. Yeah. So I'm not talking the detail about it. So in here, what I really want to point out is, if a software guy develop, you have a compiler. Okay, and then you have a processor architectures. They two combine to resolve all those data contention and give you high performance. Okay, in the compiler side, they try to reorder the instruction execution sequence. Okay, they can do the compiler level optimization, but compiler level optimization can only optimize statically. Okay, but for certain situation that dependency or contention happen, since it's data dependent, so it's happen at the runtime. Okay, at that time, that kind of optimization is done in the processor architecture. Okay, for example, the processor can do the speculative execution. For example, like a branch. Okay, they can speculate the branch. make the execution without store. A later stage, when the real data comes in and find out that speculation is wrong, then they try to recover it, or the side effect. Okay, done by the processor. Okay, but as a HLS, you don't have a compiler. The real SQL compiler, yeah, actually you have a HLS compiler doing certain kind of optimization, but you don't have a processor architecture to dynamically resolve those contention for you. Okay, so the processor design techniques, you have to know that in order to incorporate into your HLS coding. Okay, for example, for this kind of a contention, yeah, you need to apply some coding techniques to resolve it. Like this kind of write after read. For example, this example, write after read. You can see this write after read, like this one. Okay. At the same cycle, you write, also read. But you want to make sure the read is read the old value instead of the new store value. Okay. Like this one, write after write. If this thing happens, it's like this one. Okay. You store at the location B3 and you store the B3. Okay, so the previous write actually override the later write. So B3 content is not updated. Because the update value should be this one, but it's overwritten by the previous one. Okay, this kind of dependency. So for this two type of dependency in the compiler, in the computer architecture, compiler they use the renaming techniques to resolve it for you. Yeah. So if your HLS code has these two kind of dependency, then you're going to apply the same processor design techniques, which is the renaming techniques, in your coding to resolve the dependency. Yeah. Otherwise, the HLS compiler, like this one, they will move here. And for this one, this execution have to move over. Okay, and this construction, the SB3 should be after this point. So that increase, you lower your performance if you let HLS compiler handle it for you. Yeah, they have lower performance in order to avoid those dependency. Yeah. So to write a high performance HLS code, to tell the truth, you have a lot to learn. You have to know compiler, you know a lot of design techniques. Yeah. So that's one aspect. Another aspect is software execution and hardware behavior is differently. Yeah. Remember, we design. One of the reasons we use a high-level synthesis is very important criteria is that software execution result should be equivalent to the hardware result. That's very, very important. If the way you write the code, the software, pure software execution is different from the hardware, this thing is useless. Nobody going to use it, right? Yeah. So then we need to go back to the hardware execution behavior and software execution behavior, the difference between them. Then you have to write in a way to make sure the synthesis hardware behavior matches the software. Okay, so I like to take this example here. Okay, that's a very simple function here. I could probably join here, otherwise online people cannot see what I'm talking about. So let's look at this function here. Okay, that's a simple function you written in C. Okay, that's use them. And then you try to use this module, you compose the module in this way. There are two modules interconnect back to back. Okay, you have this function and this output fit to, let me grab here, to this function. Okay. So that's the I input, and you have the output temp. Okay, and the temp going to the second function, and you get the output here. So that's a very simple. That's the only single forwarding pass. This simple forwarding pass. So for C program, you execute this function, and then you evaluate this function. So the hardware behavior perform the same. So there is no problem. The hardware design will be matched the software coding, software execution. Then let's look at this example. This thing is a little bit complicated. You have a feedback pass here. Okay. Almost all the design, complicated design, have a feedback pass, like a processor. Okay, brain prediction, you have a feedback pass. Speculative dynamic execution, you get the final result and then you feedback. Okay, so all the advanced, complicated logic design, they have a feedback pass. Okay, so let's try to reason why the hardware and software behave different. Okay, in this example, there's a two function. Okay, and so that's the input, and the first function output is temp1, and the second function output is temp2, and then temp2 feedback to the to the first function. That's foo1, that's foo2. Okay, take I and temp2 coming from the second function, and generate the temp1, and the second function temp1, and generate the temp2. Okay, when you run the C program and the hardware, they behave differently. Why is different? Look at this logic. When the I input change, there's a combinational pass coming all the way here. So from I change, the temp2 actually change. But when you write this code, you execute the function 1 first. The temp2 is old value because the second function is not evaluated yet. So you are using the old temp2, not the temp2 affected by the I at the current cycle. Okay. Hope you understand why it's different. Everything here, the difference is caused by software you execute or evaluated in a sequential manner. Yeah, you follow instruction sequence and execute them. And their execution result is a blocking manner. Because next statement will take the result from the previous instructions. Okay, it's blocking. But for hardware, it's out of order, and they are event-driven. And what's important is re-evaluate. Okay, but for software programs in sequence, it will not go back, re-evaluate. Yeah, so for certain logic structure, it's very difficult to, not very difficult, actually there's a way I'm going to teach in the section structure design. Yeah. And there's a way, a C++ coding style, you can emulate this non-blocking behavior. Okay, yeah, and most of people teach HLS, they don't teach structure design, because structure design just like a barrel code. Okay, people want to write the code at a high level. Okay, if you're talking about structure design,
structure design means you describe the structure by the language, the structure. So that's what the HDL language for. Yeah. And so normally when people teach HLS, they don't teach structure design. They don't expose this kind of problem for you. Yeah. However, I think structure design is important because certain techniques certain design structure cannot really fit into the data path flow. Certain design is simply just control intensive, but you need to be able to describe in C language. Otherwise, you will run into a situation that you have a part of design is written in C, C++, and certain other part of design you have to write in Verilog in HDL. Okay, then to do the verification, you need to have a mix, Verilog code and C++. That's a code simulation. And code simulation, these two words, the C executable and the Verilog code simulator, when you combine them to run, that's run very slow, very, very slow. Yeah. And besides, you cannot expect software programmer to run Verilog simulator, right? So software programmer, they simply compile a C code and execute them. And then right now you have to tell them, oh, you have to call up the Verilog simulator and do the code simulation. You scale away all the software programmer. Yeah, so lose the purpose to teach HLS. Yeah. So that's why I have to teach structure design. Yeah, and using the C to describe a structure design. Okay, next, let's talk about the benefits. Okay, what do you gain from the? It sounds like till now you think, oh, HLS looks very complicated, and you don't reduce my effort, and then you have to learn a lot. You have to write a good HLS code. Yeah, but look at those benefits. You will worth to learn the HLS. First, is the design and verification productivities. In my past teaching in Taida for 3 semesters, and some students, they don't quite believe HLS can gain you anything. So they did the project. One is the design done by their senior with Verilog coding. And then with given algorithm, okay, because that HDL code originally written in C code, okay, and the senior spent maybe 6 months or a year to design into the hardware, and then they usually use the HLS to redesign it and try to compare the design time and the performance. Yeah, they all get the consensus, the benefit that HLS brings to them. Yeah. And then another benefit is a broader IP reuse. And also they can improve quality result. That means you use the HLS, you may get better result than using HDL, the conventional hardware design approach. Yeah. So how is possible HLS can have a better QOR than RTL code? Okay, and hopefully after this slide, you will have some understanding about this. Okay, here. So this pyramid basically outlines the whole design process. Okay, you start with the function spec with constraint given by the product spec. Okay, and then normally the architect, yeah, work on this part. Okay, they define the architecture, and then as a logic designer, you have to handle all the details Okay, and then you have to schedule operation. You have to design the final state machine, and then you do the pipeline and insert the pipeline stage and doing all the pipeline control. And to save the gate count, you have to manually to sharing all the data path components. And then at the end, you do the area reduction. Yeah. Also, that's a very tedious. This part is tedious and also error prone. So you need to spend a lot of time doing the verification. Okay, that all your life, your time spent on doing all those tedious work. Yeah, but with HLS, this part is handled by the HLS compiler, and you only focus on this part. Define, make sure the function is correct, and you choose the right architecture and given the right constraint. With this approach, this paper actually study a lot of designs. They conclude for the first design, you get 10 to 15 times faster. You shorten the design time. And it's especially pronounced if this is a derivative design. That means that's a modification of design. And it's 40 times faster. The reason why it's so fast because verification, you reduce a lot of verification time because you have to trust the compiler translate the design correctly. Okay, I think you have this belief. Otherwise, it won't be a commercial product. Yeah, all the people using this compiler, yeah, all can get the correct result. So you can trust compiler will do the right work for you. Yeah, and for the quality of a result, it's in a range. Okay, and sometimes you can get better result than the RTL coding. Yeah. Okay, so and let's talk about the IP reuse. Yeah. So when we design an IP, we want this IP be flexible and can target to different product spec. Yeah. The good thing with C++ is it's an object-oriented language. Yeah. Especially C++ provide template and class. Template and class is very important. For example, class. Okay, one of the attributes of a class is its function or structure depend on data, right? So you don't need to write, if I'm an RTL designer, okay, I need to write each function for different data inputs, different data type, for example. But if I write C+ with a class, the class can instantiate with a unique class depending on its data type. Okay, so you can write a piece of code can accommodate different type of data input instead of repeatedly write a lot of similar code. Yeah. So C++ is an object-oriented language. Yeah. And also, you use this approach, you only need to code in the functionality and microarchitecture. You don't need to specifically specify the detailed implementation. For example, finite state machine, you don't specify. And data path component, you let the compiler choose for you. And how to do the pipeline, how to insert the pipeline stage. And when you change the pipeline, you change all of the controls. Yeah. So what's the most troublesome thing is when you try to change your pipeline stage. I remember one time that our processor team in Austin, they designed the processor, which is a 20-stage pipeline. And I have my engineer to evaluate and think some of the pipeline stage is not necessary because the timing is not critical. Then that stage should be able to merge to another stage, so you can reduce the pipeline stage. So basically, we will change the pipeline stage from 20 stages to 16 stages. Okay, that basically improve the performance. And the design team in Austin say it won't work. It's too complicated for you guys because you are not the original designer. Yeah, you want to change your processor pipeline stage. No way, it won't work. Yeah. So from this statement, you know, for a design, complicated design, the pipeline, if you change your pipeline stage, that's basically the redesign effort. You have to do a lot of verification to make sure it's no missing link, no missing control there. Yeah. So it's very, very complicated, very labor intensive. So especially you spend a lot of time doing the verification. Yeah, but with a high-level synthesis, then you don't need to worry about that because that part is handled by the compiler, by the algorithm. So you guarantee no mistake. You are correct. Yeah. So with this design methodology, you can use the same IP description to target to different application area for high performance, low power, or low area. So you simply change the pragma, then you can generate the target IP design. Yeah. So it's very critical. Yeah, very important. Yeah, using high level sense. If you are an IP developer company, you should adopt this design methodology. Yeah, save a lot of engineering resource. Okay, let's talk about the improve quality of a result. First, as I said, the compiler is still evolving. For example, when I a year ago when I teach the HLS, at that time, the data forwarding techniques is not built into the high-level synthesis until I teach using the new version of a VTIS compiler. And the student told me that the source code, you don't need to restructure the code. The compiler already did that for you using the data folding. Before I teach them how to do the data forwarding by restructure the C code to do the data forwarding. And later on, the student told me, you actually don't need to do that. The result, the new compiler already did that for you. Okay. So also, if you look at a lot of paper published, actually this is quite an active research field to do the high-level synthesis compiler. Okay, if you look at the papers, I actually read some papers because I want to teach some design example to let you learn how to write high-performance C++ code. So I studied those papers. And what surprised me is a lot of very high-level, advanced design techniques has been employed in the compiler. Okay, I saw some of the design techniques only available for the high-performance processor designer because I know all those processor design. There's quite high level. I think a normal logic designer won't have the capability to do speculative execution. Yeah, so that's a very complicated design techniques. And the paper, people try to incorporate all those advanced design techniques in its compiler. So you can imagine, once those techniques incorporated into the compiler, they can generate a design better than average logic design. Okay, only a 10, 20 years senior designer, and they have to design for high performance logic like a processor design can have this kind of capability. So compiler will do better job than normal logic designer, even senior logic designer. However, these papers, techniques from the paper takes a long time to incorporate into the HLS compiler to make the automated. Okay. But what I like to teach is the techniques, because the way they do is they don't rewrite the HLS compiler. They simply take a original code, analyze, and then apply the advanced techniques and generate a C++ code output that do all the code structure for you. And then go through the standard HLS compiler. Okay, that's their approach. Okay, so before the whole thing can be integrated into the HLS compiler, you guys can learn the techniques from the papers, do the manual C code structure, incorporate into your high-level synthesis C design, C++ coding. Yeah. But in here, what I'm saying is compiler continue to evolve. They will do better job than even the senior logic designer. Okay, so you really need to. So a lot of in Taiwan, the IC company, especially big established IC company, they still stuck with the traditional design methodology. They hire a lot of logic customized modules. Yeah, then I'm afraid this approach will lose its edge, yeah, in the future. Okay, that's one thing that why you can get better quality of result. Another thing is by using this methodology, allow more design space exploration. Okay, it can do very quick. Imagine that it's tedious to do the detailed design and then spend a lot of time doing the verification. So it takes a long time in the whole design process. So it leaves very little time for the architectural exploration. Okay, you have to quickly design an architecture and move forward and doing the detailed design. But with this approach, the actual verification time gets shrink and the detailed design is done by the compiler. So you have a lot of time to explore different design space and then find out a good architecture, a good trade-off in terms of performance area and power. Yeah. So that's one of the reasons why the resultant design will be better than handcrafted RTL, because you can have a larger design space to explore and find optimal one. And this example, that's a guy's thesis. Yeah, he actually designed the following modules by optimize its RTL design or using the HLS. They do the comparison. We quickly look at that. For sub filter, HLS is worse than the RTL, but for the Gaussian filter, you get better, yeah, resource and higher speed. Yeah. So from the result, you can see using the HLS, you get more or less the same as RTL design. Yeah. Okay. Next, we'll talk about industry use case. Yeah. I would say that most, probably not all, even now all the IT big company, US IT big company, they have a lot of data center business. They try to, they have a lot of applications. So a lot of US IT company, they start doing the IC design. Okay, and their IC design definitely is application specific. They are not design commodity product like a mobile phone chip or standard graphic chip. Okay, they are not designing the standard one. They design application specific chip. Okay, and they all adopt HLS design methodology for those foreign company. Yeah, but not in Taiwan. Taiwan, only small company maybe use. So let's look at NVIDIA. So let's look at the verdict from NVIDIA. Okay, it claims it's 10 times improvement in RTL design. Okay, in terms of the design cycle, and in terms of performance, they conclude there's only less than 2.6% performance lag from the RTL design. So it's very close to the handcrafted RTL design. And in here, we notice that verification runtime is 500 times reduced. Yeah, and they also emphasize there is a rapid design change possible. Okay, those are the benefits give to you. Another example is Google designed the VP9 codec. Okay, let's look at that's the whole design structures, and the brown box is the one developed by HLS, and the blue one is still RTL, the structure design, and most of them are like a FIFO or the bus interface. Yeah, this bus interface, but the core algorithm, they are all implemented by HLS. And the advantage using this design approach is originally you have the whole system written in C language, and then you can dispatch portion of the C function to different designer to do the HLS optimization. And for each function designer, when they are done with the HLS optimization, because they involve, you have to change the C code, restructure the C code, they can pull into the whole system, doing the whole system simulation from the beginning. It's not like the traditional design approach. You have to wait for a long time for each individual module design is done, and then you do the top level integration, and then you do the whole chip verification. Then you find out a lot of bugs, and then try to fix them. Yeah, but with this approach, you can do the system verification from the very beginning. So it most takes no effort to verify it when you integrate them together. So that's another very important advantage. Yeah. So look at here, what they claim is if you written in C++, there is only 69,000 lines of code instead of 1.2 million lines of code. So simply look at how many lines of code, you know how much complexity reduction in the verification stage. And you also claim simulation speed is 500 times faster. That's the same as NVIDIA claim. Yeah. And the benefit for Google, you know, Google is a software company, so they really like software-like process. Yeah. And you can always do the algorithm change at the last stage. Yeah. So it provides the flexibility. Yeah. Okay. So it's obvious that those IT company, big IT company, they like HLS design methodology. Okay, that's another example for application in the field. So that's in the field oil and gas. So they use the RTM algorithm to find out the Earth's structures. Okay. So basically, you need to have a way to do quick simulation, a quick waveform, look at the structure based on the RTM, reverse time migration algorithm. So there's a statement here. So this, the whole thing, the Fpga design is done by a software engineer. Okay, and this guy don't have the oil and gas experience. So they simply take the RTM algorithm, the C code, and then restructure and make it run through the HLS. Okay, so it takes only 1 month to describe and implement the whole RTM algorithm in C++. Yeah. So that's another demonstration that how a software engineer can quickly adopt the high-level synthesis in their FPGA design. Okay, that's another example. Another purpose for me to teach the course is I think Taiwan need to have an industry for system house or system integrator. Yeah, right now in Taiwan, there are only big IC design company. They absorb all the talent into the big company. And actually, Taiwan students, they have all different talents. Yeah, and for the SI company, they don't actually need a lot of funding. Okay, so all you need is a brand. You have a good architecture design and you have a software skill. Then you can accelerate certain function and pull the function into a so-called application appliance. Okay, and then you can sell this product. Yeah, and today's actually there are many applications need to accelerate its speed or improve its intelligence. Yeah. So I particularly point out this this company. There's a stock company in US. This company offer a device like this one to do the natural language understanding. Okay, the traditional the natural language understanding is based on statistics and modeling. And that can give you good result, but only reach a certain accuracy, and then you stop, could not continue to improve. So people today, they borrow an algorithm from the neuroscience. They find out that when humans see a word, try to understand its meaning, and they have a different area active in its cortex. Okay, so that's the basic idea. And then they come out an algorithm called Semantic Folding. Okay, and this algorithm is very computationally intensive. So normally you need a supercomputer to do that applications. Okay, the detailed algorithm I'm not going to introduce here. But what I like to point out is, and I look at the YouTube, they interview the CEO of this company. The CEO says, my company, the core competence is not inventing this algorithm. They simply borrow this algorithm. What they did is they try to make this computation efficient. Okay, so this is their product. And they use U50. In this course, you're going to use a U50 FPGA. And they plug the FPGA in a normal, it's not super fast server. It's AMD normal servers. Okay, so they can run in very low power, so that they can cram into a low profile form factor. Yeah, and what I say is application appliance is this appliance has a two meaning for an appliance. First is easy to use. Okay, so only perform a fixed dedicated function, but it's run very efficient. Yeah. So for this device, they doing the natural language understanding. Yeah. And they don't need to, for example, in here, all the components you can from off shelf. You can buy the box, okay, off shelf. You can buy the motherboard, okay. So everything here, you just design the FPGA acceleration for their algorithm and related application software. Okay, so it's well suitable for start company, yeah, with a limited engineering resource. Then you can deliver very good product. Yeah. So I think this slide concludes my first part of the class today. So we take a break. So it's cool, okay? Actually, there are many opportunities for application acceleration appliance. Yeah. Okay, so we take a break for 5 minutes. So we come back at 11:10. Okay, good. Okay, yeah, let's start the class. So this part, I'm going to introduce the course plan. Yeah, introduce the workload for this class. As I said, that maybe some of you will drop after this part of the lecture. Okay. For this course, I set up a course objective for myself. Okay, that's the purpose of what I expect you learn. So I hope yourself, you should set this as your objective for taking this course. First, we want to design a complex digital circuit. Okay, not simple one. Okay. And I want you develop the capability doing the system level analysis and optimization. Okay, so we are talking about application acceleration. So you have to optimize from the system point of view. Okay, don't limit yourself only doing the kernel optimization. And I'd like you to develop an independent research capability on specific application areas. And then you can evaluate and develop end-to-end application acceleration. That's the requirement for the final project. Okay. So got to be an end-to-end application acceleration. So that means they involve the I/O from the source of data to the end result. At the last, I really like to promote engineering soft skill. Yeah, I have been in industry for over 30 years, and I have seen many engineers, not just Taiwan, and also China. Okay. And from my observation is the technical growth really depends on many of the soft skills, not the hard technical skill. Oftentimes that limit you. Yeah. And soft skill is very important. For example, the type of attribute I'm really look for is collaborations and problem formulation. And for problem formulation, it's very critical is you know how to ask question. In the class, I expect you ask questions. Yeah, ask the right question. That's the very important capabilities. And you need to be express idea. So I have a presentation, and you guys, I hope every one of you can stand on stage and do the presentation. Yeah, and for the presentation, it's not required that you have to speak English. Okay, it's of course encourage you to speak English, but it's not required. So the main purpose, the main goal is you need to be able to express your idea clearly, concisely, and to the point. Okay, so express idea is important. So we have a presentation to train you, and also the project planning execution. So we have a final project, and the final project is a team project. It's a bigger scope. So you need to define stages of a milestone and define the quality of each deliverable and coordinate among at least 3 members. Yeah. So how do you plan in a project and do the execution and deliver at the final result? Especially when you explore a new project, didn't do it before. You always it's always possible run into difficulties, and then you need to adjust your goal, adapt to different situations. Then you have to change your plan. Yeah, for those process, hope you can have experience in this course. Okay, there's a reference material here. For HLS, it's a new developed field that you can find out a lot of reference papers. Okay, Xilinx published a lot of HLS papers or application note. Okay, and however, they are kind of a scatter. Okay, and no systematic introduced step by step to teach you how to do good HLS design. So that's why I wrote HLS textbook in online. Yeah, you are free to study it. And that's a textbook online will be the material for midterm exam. Okay, I know Taiwan student, if you don't know exam, then you don't study. Yeah, that's my experience. Even Taida student, it's the same. Yeah, like a first semester, yeah, everything is a flip. I use a flip classroom. So in the class, there's no lecture. Actually, I recall all the material online. And but turns out after one semester, I feel they really don't learn much about HLS. And people come to question, and those questions they can find out in my online course, online video. Obviously, they didn't watch it. Yeah. So that's why I go back the traditional way, which the Taiwan student familiar with, is I have a lecture, I have a textbook, I have an exam. So hopefully we can get things going and get you really learn something. Yeah. And okay, and the following reference paper, I have find the updated one because this year, this semester I use a 2021.2 VT's version. So a lot of reference paper get updated. So I collect updated one and put it into the Google Drive. Yeah, you can simply download those. Yeah. Okay. And there are other supplementary materials they reference in lecture slide. Yeah. For all the reference, I will put like something like, yeah, a link. If you have time to study more, yeah, welcome to reference the original papers. Okay. Okay. So that's a course schedule, and this semester there are total 18 semesters, 18 weeks, and unfortunately there is no holiday happen on Wednesday in this semester. Yeah, so I look at that. Doesn't like last semester I have 3 weeks off, yeah, because there's some kind of holiday happen. So there's no class. Yeah, but this semester they're going to be solid 18 weeks. Yeah, on Wednesday. And the course is scheduled in 3 parts. The first part is before the midterm. I'm gonna to focus on HLS skill set. So for the first 8 weeks, most of them are lectures on the HLS skills. Okay, and corresponding also have a labs. Okay, the labs there's 1 week, 2 weeks, or 3 weeks, depending on the complexity of the lab. And there's a due date. Due date is a working time plus 1 week. Okay, so you're supposed doing this lab in 1 week, then you have another week of buffer before you turn in the report. Okay, so that's how the schedule is arranged. Okay, so for the lab, I expect in the first 2 weeks, you finish lab 1 to 3. They are very simple lab and well-documented workbook. You simply follow the instruction without using much brain. Yeah, just, key typing. Yeah. And then you get the result. Okay. Hopefully. Yeah, if you're missing or didn't watch the detail, you may have a typo, then you need to correct. That's your responsibility. Okay, so so the purpose of first 3 lab is pick up the platform for this semester. Yeah, there are 2 platforms you need to learn and related tools. One is for the H side for embedded system using the pink board. One is used for the cloud data center. That's a U50. Yeah. So for the first 2 weeks, you will have the tool and the board, okay, ready for future development. Okay. And then the second part, I will introduce a lab later. Okay. So the course schedule, first part is the HLS skill development. The second part, I will introduce 4 application platforms. Okay, one platform is for you to design the neural network accelerator. There's a framework called Fin. So based on this framework, you can develop the neural network accelerator, and it's a framework, so it can integrate with applications. Okay. And then there's a RISC-V. Okay, and there's a AAT. AAT is a arithmetic accelerated arithmetic trading. Okay, that's for finance high-frequency trading, and this is a good platform for other application. I will introduce detail later. Yeah, and AIoT. Yeah, so the second part of the course, I'm gonna to hand you 4 platform, and you can, based on your final project on these platforms, to develop your final project. But it's not limited. You don't have to use this 4 platform. Yeah, but it's a good platform for you to develop the final project. Okay, the third part, the time, basically I want you to get involved in the final project as early as possible. So the third section of this course, you mainly work on the final project. So in the meantime, I will also have some lecture to summarize or apply all the HLS techniques in some advanced topics. For example, application acceleration best practice. And I will introduce some architectural design example. So let you to know what the right architecture should look like. I propose a framework to develop the HLS accelerator. Yeah. So what you learn here, you can apply that in your final project. I should teach you this earlier so that yeah, you can use a lot of techniques here in your final project. And here, what I don't know is this is suppose the last week in the semester, the 18th week. Okay, that's a final exam week. And here I saw the calendar says for graduate, I have to give the grade by this week. I originally intend to present the final project in the following week. Yeah, but due to that, I don't know whether I should have some graduate, because their grade has to be turned in this week. So they have to give the presentation earlier, 1 week early. Yeah. They haven't decided yet. Yeah. So you should expect the final project is in either this week, June 15 or June 22nd. Yeah. Okay, so that's the timeline for today's for this course. So that's the textbook. Yeah, that's the topics I am going to teach in this semester. Okay, I talk about 4 platforms. Okay, one is the Fin. Yeah. The Fin is a framework, and you can build end-to-end hardware accelerator. Yeah. using the techniques, data flow, and customized precision. Yeah, as I said, the FPGA offer the advantage in the data flow architecture and customized precision. And this framework offers these two advantages so that you can design, optimize, customize, and optimize NN accelerator. Yeah. So I will have the developer, not the developer. I have in that semester I have 2 students to learn this thin framework and develop a course, and it's associated lab. And I will invite them to teach in this class, yeah, for this framework. And there's also a lab design for it. So the purpose is let you to pick up this framework. You know how to use this framework to design your own network. Okay, another one is a RISC-V. This RISC-V is developed by C++. Okay, so here I like to say for any new processor development, you have a ISA, instruction set architecture. Okay, and then based on the instruction set architecture, you design an instruction set simulator. Okay, the instruction set simulator is gonna be a golden architectural reference. So based on that, you can design your processor architecture. But for whatever implementation, the result you have to conform to the instruction set architecture spec. Okay, so the compatibility is the most difficult part. For example, in x86 architecture, and a lot of thing is undocumented. I remember our processor team in Austin, they try to reverse from the Intel processor. Okay, so after each execution, all of the architectural register and status, every bit has to be matched. And what's more difficult is exception. When exception happen or interrupt happens, then how the CPU pipeline behave. Okay, so those are compatibility issue. A lot Intel doesn't document. They have an instruction set data book, but a lot of things not described in the data book. So they spend a lot of time to make sure the processor design is that it compatible. Otherwise, a lot of software already running in Intel processor. If they got different result in your processor will have no sale. Nobody will buy your processor. Yeah. So design a new processor is very important. You must have an instruction set architecture. So the idea is, why not we directly take the instruction set simulator, which is written in C or C++, and turn it into a design. And the compiler guarantees the correctness. That means the hardware implementation will be same as the C code execution. For that, you quickly have a compatible processor, right? Yeah, so that's the idea. People develop the RISC-V processor using the C++. Yeah, and I particularly emphasize this MCU. I think this MCU, although it's a very simple, only doing the integer instructions, and only 5-stage pipeline, but it's very important in every application acceleration at the edge end. Okay. Remember that we have an application program that when we do the acceleration, we partition parts, okay, put into the FPGA. And the other part is a remote host. And you all realize there are a lot of overhead in doing the data movement, right? You also realize once the FPGA acceleration is in another device, they are running in different address space. So a lot of overhead involved. Okay. So there are 3 locations in pull your acceleration device. Pull into the I/O device, like a PCIe device. That's one place you can put the acceleration device. Another approach is pull on the CPU bus. Okay, that like an Intel front-side bus, people actually plug in the FPGA card. Okay, it's closer. Okay, however, there is still data movement, but the data movement is on the CPU front-side bus. It's much faster than the PCIe I/O bus. It's closer, so that means the latency is reduced. Okay, but the most power-efficient way is put the accelerator inside the processor pipeline. Okay, there are several advantages that they're actually running in the same address space, and they share the same memory and register files. Okay, so that's the optimal place. In that case, you really need to have a control over a microprocessor. So if you have a microprocessor and you design a customized instruction set, okay, then you can have a really low power edge device for AIoT application. Yeah. So for this, RISC-V take you one step further from simple accelerator design, and then you integrate with processor. Yeah, I really look forward to some team can pick up this design. For example, you simply implement a vector processing unit, because the AI a lot of time, just a vector processing. Yeah, RISC-V has a vector extension instruction set. You may just implement that instruction set based on the HLS RISC-V code. If you're really interested in computer architecture, so that's one platform. Yeah. Another is AAT, accelerated algorithm trading. So here, this is a framework offered by Xilinx. Xilinx actually provide this FPGA with those module design in HLS. They also provide the related drivers. So they have Xilinx provide the whole framework here. Okay. So originally, this platform is offered for doing the this accelerated arithmetic trading. So inside here, you have the network packet processing. So they put all the Ethernet TCP/IP packet processing in the hardware. So there is no driver involved. So the network comes in, and before people, the network packet simply save in the memory, and then CPU read the memory, read all the packet, and passing those packets. Yeah, and in here, all the passing, network packet passing, and the TCP/IP protocol is handled by the hardware. Okay. And this Ethernet TCP/IP offloading is written in HLS. That's quite complicated code, but there's a source code there. You don't need to study that. Yeah, just be able to use it. And the next, you have line processing and market data passing. Everything all the way to order book, set up, build up. And then the pricing engine, and then pricing engine, you implement all different sort of a strategy in C++ embedded in the FPGA, and then you generate the order. The order sent out to the Ethernet layers. Yeah. So they provide the whole framework. Yeah. So for that, for those people interested in finance, you may consider that. And this framework has a very wide application. I can see that it's not only used for high-frequency trading, that you can use any sort of a distributed and scalable application acceleration. You can imagine you have a Fpga acceleration. Originally, people plug into a server on the PCIe bus, right? And that's a computing resource. Because we know a lot of application is from the network, okay, and your data from the network, okay. So you want to provide application acceleration in a distributed way, distributed parallel processing, okay. And normally people put the accelerator card in a server, and the server connect to the network, right? So when a network requests, I want to do certain kind of application acceleration, then software, the server side, read the network packet and dispatch to the FPGA. So it takes a longer time and much higher power. Okay, so why not this PCIe card, accelerator card, the front side is an Ethernet connection. You directly connect on the Ethernet. So when the network packet comes in, you have a hardware network packet passing and directly doing the computation and return result, just simply like this high frequency trading. Yeah. So it gives you much lower latency and run much faster and lower power. And you don't have a big server at the front. Okay, so I can imagine with this platform, you can enable a lot of applications. For example, besides the arithmetic trading, you can doing the market information analysis. For example, you can subscribe some RSS feed all the market informations. Okay, then you pass in all the text, grab the key data. Okay, and then you can quickly find out what happened in the world. Yeah, real time. Yeah, passing. For example, that or advertisement bid. Yeah. So I think that this platform can have a wide applications. Yeah. Next platform is AIoT. Yeah. So this is a framework that you can quickly integrate a lot of IP in your pipeline stage. Pipeline stage means, for example, you have a certain task to do, then they have a stage of a workflow, different stage of processing you need to do. Okay, so each stage is a kernel function. You can accelerate it simply like this part. Okay, you may have a kernel doing the NN accelerator, and you may have a signal processing. Yeah. Okay. So for each kernel function, the traditional way, the working model is at each stage of a kernel function, the result you will save into the memory. And then from the memory, you pipe to next stage of processing. And then you use the whole CPU to do all the synchronization and control. Okay, so that's a longer time and higher power. Yeah. So it's better that for each stage, you use a stream interface. And then from previous stage, you stream the data to next stage without going through the system memory. So you use the intermediate swing switch to connect them. Yeah. So hardware-wise, this concept, and then actually the whole thing is developed using software approach. Okay, in software, you simply call each function step by step, right? Yeah. So you develop this whole hardware using the software approach. You actually use a software to integrate everything together. Yeah. and compose the pipeline stage. So for this platform, it can last semester in Taida, people based on that doing the final project. So they have a video stream using HDMI in and using the computer vision, CV, OpenCV to do the image processing, doing the scaling, and then fit their NN network. NN network is developed by Fin. Okay, so they do the gesture recognition. And the final result, the gesture result, they can display, come out, output. Yeah. So they use the configurable, composable pipeline, yeah, to compose the whole system. Yeah. So that's another platform will be interesting that you can develop for your final project. Yeah. Okay, for lab. Okay, first, I believe you already installed the tool, okay? And we're going to use the new version, 2021.2. And there are 3 tools. One is VTIS HLS, one is the Vivado IP integration, and the VTIS IDE, yeah. So you use the first tool for the pink, okay? And then you use this tool for doing the U50 cloud applications. Yeah. But most of the time, you will spend a lot of time in VTIS HLS. So you use this tool to do the C simulation, to do the code simulation, and optimize your HLS kernel all in this tool. And when you want to compile a final scalable, you either use a Vivado IP integration to compose the final chip bitstream file, or using the VTIS flow. And VTIS, we will also use a lot of tool offered by the VTIS in the IDE environment. It can do all kind of analysis. For example, like the performance analysis or the data flow analysis. So in this course, you need to learn a lot of analysis too. And when you develop the final project or doing the project report, you will use those analysis to find out the insight. What do you find from this analysis result? And then what your solution to improve it. The procedure you learn from using this tool will be presented in your lab presentation. Okay. For this course, there are 2 lab platforms you're gonna to use. One is Pink Z2. That's a MPSoC. MPSoC, that means the Fpga integrate with the SoC. SoC has a processor. For Pink Z2, it has 2, I believe it's A9 processors. Not very powerful one. There's a very low cost, low end MPSoC, but it's good enough for our course. And that MPSoC will be used for embedded systems. Another platform is U50. And that's for cloud application. U50 is a PCIe accelerator card plugged into the server. Yeah. And I forgot, you probably need to introduce the logistics, so I need to finish quick. Okay. And again, for this course, we have 3 groups of labs. The first group of lab is lab 1, 2, 3. These 2 labs, the 3 labs, is basically teach you to do the tool installation and build up the basic environment. Okay, so you will implement a very simple IP design. Okay, and then you will also deploy to the Pink FPGA board, and then you use a Jupyter notebook to communicate with this FPGA board. Okay, so the lab 1. So the purpose is not teach you HLS coding, simply that you're familiar with the tool and the device. And lab 2 do a little bit further that you have a FIR design, okay, and then you experiment different interfaces, okay. And the lab 3 is the U50, which is a PCIe card, and then you will use the VTIS platform and using the OpenShield, and that's the environment people use to develop cloud applications. Yeah. So if you have an Amazon account, if you like to use Amazon Fpga, you probably go through the same similar flow like this lab. And for this lab 2 and 3, the source code is a very good template for you to develop other application. Okay, so if you want to do another application acceleration based on U50, then you can reference the source code of the lab 3 code, use that as a template and make an appropriate modification. Okay, since you already make this lab 3 works, then you do the change. As long as you follow basic guideline, then likely the new application accelerator will work. Okay, the lab 2 will take you one step further to do advanced tool usage and teach you more about the kernel optimization, and especially it teach you the software and hardware system code design. Yeah. So there are 3 labs. Lab A borrow from the UG A70. Okay, so you have all the code ready. Okay, you simply follow the instruction here. Okay, the U87 is a document. It has each chapter has some lab with a very detailed description. So I only pick these chapters because I think it's more relevant to what you are learning. Yeah. And another part of some lab from the VTIS tutorial. Okay, and this part is more focused on HLS kernel only. Okay, this is more about the software hardware code design. Yeah. And for this lab, each of you pick one. Okay, and then we will pick a student to give a presentation on these topics. Yeah. So when you do the presentation, it's not like you do the presentation in your with your advisor. Okay, for those kind of a presentation, you simply update your status. Okay, but for the presentation in this class, it's teaching. Okay, important. You have to teach what you learn and make other people understand. Okay, so always think the best way to learn is to teach. That's the reason why I teach HLS, because I want to learn HLS. Yeah. So so for this lab A, it's an individual lab. You pick one subject, and then you do that, and you will be selected to present in the class. Yeah, so that every one of you can learn all the topics here. Okay. Lab B is more about algorithm and design example. Okay, and so there are some lab from VTIS tutorial, and another there's a textbook PP for Fpga. It's introduced a lot of algorithms, and those algorithms quite fundamental to many algorithms. Okay, like a Codec, that's for scientific communication, DFT, digital Fourier transform, or sparse matrix vector, or matrix matrix multiplication. So those algorithms being commonly used by many algorithms. And this textbook has a very detailed algorithm description. and there are some design architecture involved. So I think it's a good material to learn that. And that will serve as a basic building block for you to do more complicated application acceleration. Yeah. So this lab mainly teach you HLS design and algorithms. So again, you pick one topics, and there are some reference code there. You try to bring up them, and then doing the analysis to understand the algorithm, and to do using the VTIS tool to do the analysis to find out the bottleneck. Okay, and then see why, how to optimize it. Yeah. So I think it's a very good material here. Okay, for lab C is a bit more complicated. This is gonna be a team project. Okay, in this class, we have 3 people in a team, and that's basically develop a VTIS library. And this VTIS library has a 3 level. Level is individual functions, and level 2 is a kernel. That means the kernel gonna to communicate with the host application. Okay, the host application will be the level 3. Level 3. So for this, actually, eventually, you will run a benchmark. You can regard the benchmark is the application program. So for this lab, after you done this lab, you have the capability to do the end-to-end application acceleration. And we use the VTIS library. And VTIS library provide the following libraries. Okay, I'd like you to, each team pick one library items. Yeah. I find out that for EE or student, they all pick like signal processing or vision. Yeah. But actually in the real world, there are a lot more applications in the world, especially in the social network space that involve the business intelligence. Yeah. And doing all kind of data mining. And for those fields, most of the EE students, they don't explore. I feel you should spend time to explore those areas. That's a lot more interesting, a lot of problem to optimize for. Yeah. So in this lab, I will kind of enforce you to, for each team, don't all select the vision library. Yeah, I will distribute that. Yeah, so that you guys will have a idea in different application area. Yeah. Okay, so that's the third group of application case. In here, you don't need to do those lab, only the lab D, the fin. I really want every one of you to pick up the fin framework to design the neural network. And for others, they are option. Yeah, you don't have to do that. That's an extra credit. If you are doing a final project based on AAT or based on ALT, then you do that lab. Yeah. Okay, but that's not required. That's otherwise too much workload. Yeah. So that's the fin. For the fin, you will design a customized layer and integrate with the whole neural network. Yeah, and then you will do all kind of analysis, explore parallelism, and you do the compiler integration. Yeah, those things won't be too difficult because there is a detailed workbook. You just run through them, and then you will work. It will work. Okay, level E is RISC-V. Okay, level F is the AAT, and that's the AIoT. Yeah. Okay, and then there is a final project. And for the final project, you can, based on the framework, lab D to G, or I will give you a lab reference list. Yeah, and you can reference that. Or you can further extend the lab C, extend to the application levels. Yeah, or you can bring your research. Yeah. You can bring your research topic to your final project, but there's a requirement. It got to be an end-to-end application acceleration. And typically, you have an application code available, a source code, okay? And then you will profile and identify the function to accelerate. And then you partition on the software part and hardware part. And the software part, you need to do optimize for parallelism and as well as the kernel optimization. Yeah. I would suggest you start thinking the final project from the very beginning. Yeah, you try to research the topics for your final project. Okay, and the last is the soft skill. Okay, soft skill, how to get point for soft skill? In here for TA, so for student raise question or answer question, you make a mark. Okay, and so for you to participate in Q&A in class, or in the class management system, there is a discussion forum. Okay, you are always ask question there, and people also offer help or offer answer in the forum. Then you will count the point. Yeah. Okay, so you offer help to solve the question. Or have a textbook. When you read a textbook, you have a feedback. Yeah, it's welcome. You give me the feedback. Yeah. Okay. Okay, and that's at the last is the grading. Okay. For the grading, the total final grade is 115 points, and that's because I have an actual grade for you to do the lab A/B presentation, or you do the actual lab, EFG, and the soft skill. Yeah. So that's how we do the grading. Yeah. Okay. So the last, I will have a TA to talk about the lab logistics. That means how do you access those FPGA board? Okay, and also lab 1 and 2, right? Okay.